Next, we are going to talk about the remainder theorem and the factor theorem. So the remainder theorem tells us if we have some polynomial and we divide it by x minus k, then the remainder is exactly the same thing as if we plug in k into the function. And this doesn't maybe seem very exciting. But hang with me and we'll see how it works, and then we'll see how we can use it in a little bit. Okay, so in this example, we want to use the remainder theorem to evaluate the function at x equal to -2. So we're going to divide this polynomial by -2. So, right, we start off by writing in the coefficients. So 3x cubed, there's a 3, 8x squared, 5x minus 7. So I bring down the 3. -2 times 3 is -6. 8 minus 6 is 2. -2 times 2 is -4. 5 minus 4 is 1. -2 times 1 is -2. -7 minus 2 is -9. So this is my remainder. And that tells us, the remainder theorem says, okay, so at x equal to -2, my function value is -9. Which means that the point -2, -9 is a point on the graph. And I can check it by actually doing what most of us would do. If somebody said to me, hey, find the value of this function when x is equal to -2, I would just put x equal -2 in my function, right? So -2 cubed, right? Put that in for x, I get times 3 plus 8 times -2 squared plus 5 times, right? So just like that. And then -2 cubed is -8, -2 squared is 4. And then I do my multiplication and I get this, and I do the addition and subtraction and I get -9. And sure enough, the point -2, -9 is on the graph. Okay, again, it doesn't, when I first learned this, I'm like, well, that's not really that helpful. Okay, but what if the remainder is 0? It turns out that now the remainder theorem actually comes in handy. So let's divide this quartic by x minus 2. And when I do that, right, again, bring down the 2. 2 times 2 is 4. Add those, multiply, add, multiply, add, multiply, and I end up with a remainder of 0. So what does that tell us? Well, it says that the point 2, 0 is a point on the graph. So 2, 0, because the y coordinate is 0, means that's an x-intercept. Well, if that's an x-intercept, then that means that 2 is a root of the function. And also, right, if we divide something and the remainder is 0, that means it's a factor, right? If I take 12 divided by 3, right, and I get 4, well, that tells me that 3 is a factor of 12. If I take 12 divided by 5, right, I get 2 remainder, I'm sorry, 2 remainder 2, which I can write as a fraction, 2 2/5. Right? 5 is not a factor of 12. So a remainder of 0 tells us that it's a factor. So now, this is kind of useful, right? We know 2 is a root. We know x minus 2 is a factor. This could actually be some useful information. So the factor theorem says that you can test whether or not something's a factor by evaluating it at that k and if the results, and you know, we actually know this already also. But let's look at an example and see how we can actually use it to factor something. So show that x minus 2 and x plus 3 are factors. So we're going to divide this by x minus 2, which is what I already did, right? We came up that 0 was a remainder, so negative 2 is a factor. So I'm left with this, right? I'm left with 2x cubed plus 11x squared plus 18x plus 9. But right, I can just use those same numbers. Now I want to see if x plus 3 is a factor. So I'm going to put, right, x minus negative 3. So I'm going to put negative 3 there. Sorry. Okay. And I divide it out. Oh, and look, I have a remainder of 0 again. And now I've got 2x squared plus 5x plus 3. And this I can factor. It's a quadratic. So, right, a times c is equal to 6. And I need something that adds to 5. So, 2 and 3. And then I have to divide by my leading coefficient. And then, right, and this simplifies, and I get x plus 1, 2x plus 3. Okay, so what if I want to check this? Well, I can do synthetic division again. For x plus 1, I need minus 1. So I bring down the 2, minus 2, get 3, minus 3, a remainder of 0. And what I'm left with is 2x plus 3. So, how do I factor this polynomial? Well, there's my answer. This is the complete factorization of f of x.